In this section, we'll study about stochastic matrices. Let's begin with a definition, probability vector, and stochastic matrix. Consider a vector P having n entries, each of which is non-negative, and some of them is 1. Then we call it a probability vector. Each entry is a probability. A stochastic matrix is a square matrix whose columns are probability vectors. It will be used to apply from the left side usually. So in the case, we indicate left stochastic matrix. And sometimes stochastic matrix can be multiplied from right side. Then we try to do here right, so right stochastic matrix. The default is left stochastic matrix. Such a stochastic matrix is also called a probability matrix, transition matrix, substitution matrix, or Markov matrix. Here we have a lemma. If P is a probability vector and T is a stochastic matrix, then their multiplication TP is a probability vector. Okay, here we have V1 to Vn, the columns of T. Then this matrix vector multiplication can be written as a linear combination of columns of T. So that is the fundamental idea in linear algebra. Of course, the coefficients must be from the vector. So we have that. Now, if we name it by Q, then we have to show each entry of Q is non-negative, and also the sum must be 1. But a non-negativity is quite clear because every entry of this metric and vector is non-negative, so that their linear combination must be non-negative. And now let's check if the sum is 1. Sum of Q, that is, Q is the same as that. Now we try to sum vertically for each vector V1. Sum of V1 entries must be 1 because it's a column of the stochastic matrix T. So each column is a probability vector. So sum must be 1. Again, sum of V2 must be 1, and so on. So we reach this summation. But we start with the P being a probability vector, so the sum must be 1. So we prove the lemma. Okay. Now we define Markov chain. A finite Markov chain is a sequence of probability vectors x0, x1, x2. So here, from x0, a probability vector, and now T, a stochastic matrix, will be multiplied to get x1, like that. Again, from x2 in this state, for x2, from x1, T is multiplied. Again, to x2, T is multiplied to get x3, and so on. We can rewrite these conditions as a recurrence relation. So xk plus 1 is t xk. The vector xk is called a state vector. So the Markov chain is producing a new state just from the last state only, xk, and the Markov metric is multiplied to get new state. Okay, in the case it is called a Markov chain. Now we will try to find and figure out eigenvalues and eigenvectors of such stochastic metric. Okay, p-norms are already defined. For example, the vector x1 norm is addition of absolute values of entries, and x2 norm is the Euclidean norm. T is a stochastic metric. Then the application of T for vector, once the magnitude is measured by one norm, then it is not larger than the x1 norm. So it is a useful theorem. So let's try to prove it. We'll begin with the proof when n is 2. Then t can be written in this way, t11, 21, and t12, 22. And also for x, we have two components, x1 and x2. Okay, here tx, one norm. One norm is addition of absolute value. Once you perform tx, then that will have two components, and that is top, that is bottom. And absolute value will be added. So from the definition, we have that. Now, x is a general metric, so that we can make it this way. For each one, now t11, t12 are non-negative, but x1, x2, at least one of them can be negative. So we have such terms along with that inequality. You can understand this one from high school mathematics. And for the other term, the same. Now we reorganize for x1 absolute value. We have two coefficients, t11, t21. For absolute value of x2, we have coefficient t12, t22. Okay, so we recheck this one. Now, T is a stochastic metric, so that sum of each column is 1. So sum must be 1, and sum must be 1. So we recheck this, and that is definition of x1 norm. So we have tx1 norm is bounded by x1 norm. That's exactly this one when n is 2. However, for general n larger than or equal to 2, this argument can be utilized exactly the same way, so you can complete the proof. This theorem will be useful to prove this corollary. For a stochastic metric T, eigenvalues must be bounded by 1 in modulus. That means once lambda is an eigenvalue of a stochastic metric, then absolute value of lambda is bounded by 1. Okay, we start with TV is a lambda v. Okay, TV1 norm is now lambda v1 norm from this equation is quite true. And then now for norm, vector norm, scalar multiple can go out with absolute sign. So these are already we know. And then now by using that theorem, tx1 norm is bounded by x1 norm. So the tv1 norm is bounded by v1 norm. Okay. And so this quantity is bounded by that one, same v1 norm. If we cancel these two, then lambda absolute value must be bounded by 1. That's exactly this one. Not complicated, right? Now, we'll try to see, and the number 1 is an eigenvalue of a stochastic metric. T is a stochastic metric. Then the number 1 is an eigenvalue of T. So for every stochastic metric, 1, the number 1, is an eigenvalue. We'll see proof, and we'll try to prove the theorem in 2 different ways, because the proof themselves will be useful for you later on. Okay, the first method, we first recognize, and the determinant of a metric is the same as the determinant of the transpose of the metric. So that is T minus lambda I. For the transpose of that, we have T transpose minus lambda I. Their determinants must be the same. That means characteristic equations are the same, and all eigenvalues are coming from the characteristic equations, so that eventually T and T transpose have exactly the same eigenvalues. Now for that metric, we consider the all ones vector. Every entry is 1. Now we multiply T transpose to all ones vector. Look at here. For T vertically, if you sum vertically, then each column will make addition the sum 1. But for T transpose, now this metric is transpose, so that now horizontally the sum is 1. This all ones vector multiplication is the same as summing these entries horizontally. So that is exactly 1 from each one. Each row we have result 1, 1, 1, 1, 1. That means all ones vector. Okay, so this equation is true. That means T transpose has the eigenvalue 1. So the 1 is one eigenvalue of T transpose. That means the number 1 is also an eigenvalue of T. So we proved it. Now go to the second method. Now let's do it with through the construction of T minus lambda I with lambda is 1. T minus lambda I, here lambda is 1. Then explicitly we can write in this way. Now we apply replacement operations. The replacement operations are not changing determinant, but the metric will be different. the same determinant. Okay, let's do in this way. Replacement. This row is added to the bottom. And again, second row, third row, every row from here to there, these rows are added to the bottom row. There are n-1 replacement operations. Each replacement is not changing the determinant. But after finishing these replacement operations, okay, let's add them. Then we know this column is 1 and minus 1, so that it will become 0. The second column, again, using the same logic, the bottom will become 0. So all the way, the bottom row will become 0. With this, the operations, the determinant must be 0. Because one row is completely 0. Its determinant is 0. But the determinant is the same as the determinant of t minus identity. That means determinant of t minus identity is 0. This implies that 1 is an eigenvalue of t. So by using the second method, we prove that. The eigenvector corresponding to the eigenvalue 1 is called a steady-state vector of the stochastic matrix. It is also called a Poron-Frobenius eigenvector or a stable equilibrium distribution. Such a steady-state vector represents a long-term behavior of a Markov chain. And because it's not changing in Markov chain, the stochastic matrix is multiplied, but it's not changing. So that means the steady-state vector represents the long-term behavior. Right? Now, how to find a steady-state vector? By definition, the steady-state vector should satisfy that. Now, algebraic manipulation, and then we recheck that one. This is a homogeneous equation. X is 0 is a solution, but to get a non-zero solution, this must be singular. That means determinant of t minus identity must be 0. But we already know that, so we can find a non-zero vector. Once a non-zero vector is found, then we scale. So addition divided by the addition of entries, then the result for the resulting vector. Now addition of the entries will be 1. So it becomes a steady-state vector. Simple, right? Now, once we found a steady-state vector, the question is it unique? That's the question. To answer the uniqueness of a steady-state vector, we'll consider the new concept. Here, in definition, we'll try to define regular stochastic matrix. Now, in this way, a stochastic matrix is regular if some metric power, so tk, for some k, tk contains only strictly positive entries. In some power, every the entry is positive, then later on always positive, so that at some point every entry is positive, then we say is regular. Okay, rather than T itself, we are using TK is here. The basic idea is around here. Now, in Markov chain, we start with the initial state, and then by applying the stochastic metric T, we reach at x1, and then again from this last state, apply T to get x2, and so on. We're moving in this way. Then, now at some, okay, now xk rather than T. After k step later, we reach at xk. But, okay, this can be written T squared x0, so that for general xk, it can be written tk now x0. So here, if we consider Markov chain, then most interesting component is steady state behavior. So the long-term behavior, so that the steady state vector is important. So then in early several steps, even though the power of T is not strictly positive, and we ignore these several steps, and then later on, from a certain moment, the entries are strictly positive, then we use that. So regular stochastic metric is defined along with TK, right? Okay. T is a regular stochastic metric. Then T has a unique steady state vector Q. So we'll not try to prove that, but once the metric is regular, then steady state vector must be unique. Furthermore, the entries of Q are all strictly positive. And also, we can find the steady state vector by using the power method. From any probability vector x0, we multiply T again, just power method. Then this is converging to the vector corresponding 1, largest eigenvalue. Eigenvalue cannot be larger than 1. And number 1 is the largest eigenvalue in modulus. But the convergence means that there's no other eigenvalue having the length 1, so that we have this convergence, the unique steady state vector. Once the metric is regular, then it's guaranteed mathematically. Okay, we have a remark. T is a regular stochastic metric. Then, now, okay, here, if lambda is an eigenvalue, then absolute value lambda is bounded to 1. This one is true for every stochastic metric, and for regular stochastic metric, here columns of TK, all columns, every column is converging to U. So if you multiply TK itself again, then every column will converge to the unique steady state vector. It's quite interesting theory, and you will prove that. And now in exercise A, here you will use that. Try to use this one, and then you can prove that. Okay. Okay, we have an example. Find the eigenvalues and eigenvectors of the Markov matrix. Here, sum is 1. Again, sum is 1. So it is a stochastic matrix. Now we are using Python. Okay, in the beginning, we define the t, and now find the eigenvalue and eigenvector by using the built-in function, and here we print. And then for the first vector, we scale by dividing by the sum of the entries. We can finish the computation of the state vector, and we print out, and that is corresponding to this one. Okay. Now after that, now we'll try to use the power method and start with this 1, 0, 0 probability vector. We multiply t again, and try to get the state in each iteration. Okay. Now that is by using built-in function. We have 1, 1/3, 1/6, the eigenvalues, and corresponding eigenvectors. By scaling by the sum of these entries, and we can get this state vector. This and that, these two vectors are parallel. And this is a state vector. Okay, now from initial probability vector, these are output of power method after multiplication of t once, twice, okay, and then up to 10 times. Now from 9th, we reach out now apparently the state vector, but this display is along with only 4-digit accuracy. Now look at the error. In some sense, from 0.3, these quantities have error. For example, 6.3 and 2.1, and now 0.7 and 0.2, and so on. As you can see, roughly, the error reduced by 3, 1/3, and again 1/3, 1/3, 1/3, and so on. This is a power method, so that the convergence speed is now governed by the factor lambda 1 on the bottom and lambda 2 is on the top. And this quantity is the convergence rate. For this problem, right now, largest eigenvalue is 1, and second one is 1/3, so that is here 1/3. So each time the error is reduced by this factor. Okay. Okay, we have the final remark. Some eigenvalues of a stochastic metric can be negative. For example, the first row, second row is reassigned from second row, first row. So it is a row interchange operation. Once you try to get the eigenvalues, then in fact the determinant is negation of the original matrix T, which means that at least one eigenvalue has a negative quantity, and so that some eigenvalue can be negative, but along with this low interchange, yet the result is a stochastic matrix. Every entry is non-negative and sum is still 1, so that is a stochastic matrix. However, the eigenvalue is changed. Okay. Okay, here we have true or false problem. Okay, T is a stochastic matrix. Then the steady-state vector is an eigenvector of T is true. And every eigenvector of T is a steady-state vector is not true. Only the eigenvector corresponding to the eigenvalue 1. The all ones vector is an eigenvector of T transpose. It's true. By using this fact, we try to prove that number 1 is an eigenvalue of T. The number 2 can be an eigenvalue of T or T transpose. Here, the can be is a trick. However, no matter how the eigenvalue of T or T transpose cannot be larger than 1 in modulus, so that 2 cannot be an eigenvalue. So it is false. All stochastic matrices are regular. Is false. Okay. You can find this quite easily. Look at identity. Identity matrix is 1, 0, 0 everywhere and 0, 1, 0 everywhere, like that. If you add columns, then all is 1. And every entry is non-negative, which means identity is a stochastic matrix. But if you multiply k times, any k, how many you multiply, it doesn't matter. It's always identity. That cannot be having all entries positive. So that this is a stochastic matrix, but not regular. So it is false. This is a simple, easiest example. Okay. Okay, that's the end of the section and end of the chapter. Thank you.